Okay. Good afternoon. Welcome again to the Chrysler Pavilion. Now we're going to talk about the importance of the Paris Agreement for preventing the sea level rise. And we welcome the next speaker, Professor Chris Stokes from Durham University, who will talk about his research on topics of ice sheets, glaciers, and sea level rise. So, any questions, please, after his presentation? We can take some questions from the audience. And so now, please welcome Professor Chris Stokes.
Thank you very much, Sebastian. So today I want to say a little bit of research, tell you a little bit about my research and the research we've been doing on the East Antarctic ice sheets. And for those of you who want to read a bit more, about it, thank you. So for those of you who want to read a bit more about the paper, it was published just a couple of months ago. There's an international team of authors with some of my colleagues in Durham, but others from all over the world. And I think the first point I'd like to make at the start of this talk is that ice sheets can cause very rapid rates of sea level rise. The animation on the left here is showing what happened to the ice sheet in North America at the end of the last ice age, about 21,000 to about 11,000 years ago. And you can see in the panel on the right there that sea level rose by 120 meters over that entire period. And some of that was contributed by Greenland ice sheet shrinking a bit. And some of it was caused by the Antarctic ice sheet shrinking a bit. But most of that sea level rise was from North America. And the curve there shows you that at some points during the deglaciation, there were quite rapid jumps in sea level. One of them is labeled there, meltwater pulse 1A. And what that shows is that sea level could have risen at about 4 meters per century. Okay, so that is 10 times current rate of sea level rise. So I think it's really important that we just start off this session really thinking about the fact that ice sheets can respond very rapidly to climate forcing. If we look at sea level rise today, as I said, it's around about, let's say, 4 millimeters per year. We know that it's doubled, that it's accelerating. We know that the contribution from both Greenland and West Antarctica has accelerated over the last few decades. And we also know that the cause of this mass loss or this ice melting is due to atmospheric forcing, whereby atmospheric warming is causing the surface of the ice sheets to melt. But also, we know that ocean warming around the edges of these ice sheets can weaken the floating portions, cause thinning of the ice, and that leads to an increase in ice discharge. And actually, that's something that Flo will be talking about a bit later in this session as well. And if we look at the Greenland ice sheet as an example, what you can see from this plot is that Greenland's losing mass. It's losing mass quite rapidly. But there's a roughly equal proportion of mass loss from surface melting, from that atmospheric warming, and a roughly equal contribution to the mass loss from the warmer oceans and a kind of dynamic mass loss as well. So they're about 50-50 in Greenland. If we look at Antarctica as a whole, then there's very little surface melting there. So that component, that mass loss from surface melting, is not a major part of what's going on in Antarctica. What's much more important is ocean warming. And it's particularly important in the West Antarctic ice sheet. If we think about the East Antarctic ice sheet, then the IPCC recently concluded that really we're not too sure what's going on in East Antarctica. And so if we look at the recent plot of an assessment of Antarctica's mass balance or mass loss, you can see the purple curve, which shows the overall mass loss from Antarctica. And very close to that is the green line, which is the mass loss from West Antarctica. So West Antarctica is dominating the sea level contribution from Antarctica at the moment. The Antarctic Peninsula, the red line, that's also contributing a bit to sea level rise, but there's not so much ice on the peninsula. But if we look at the orange or yellowy orange line, you can see that's the East Antarctic ice sheet's mass balance. And it's kind of hovering along at zero, but there are quite large uncertainties there as well. And so at the moment, or certainly recently, it's not been clear to the extent that we should be worried about East Antarctica. Is it going to just carry along in this kind of equilibrium state? Or could it start to contribute to sea level rise in the near future? And that was really the topic of the work that we did. And we looked at past warm periods, we looked at the current state of the ice sheet and of future projections. I do think it's very important that we start to consider East Antarctica as a potential source of sea level rise. It's the world's largest ice sheet. It stores an equivalent of about 52 meters of sea level rise. So it's an order of magnitude bigger than West Antarctica. It's a very big ice sheet. It actually extends to quite northern latitudes as well. So it does have a little bit more surface melting on it than we might expect. Interestingly, though, there's an order of magnitude fewer publications. I just did a very simple search at the number of papers that have been written on these ice sheets, and the black lines there are from West Antarctica, and there's over 1,000 publications. East Antarctica, far fewer publications. And there are actually some very good reasons for that. If we think why, I think there are three main reasons. The first one is that when we look at the current estimates of mass balance, they tend to be in equilibrium or perhaps even gaining mass. And so we've been far more concerned about what we've been seeing in Greenland and West Antarctica. So on this plot here, which we produced, each of those boxes represents a study. The length of the observation is on the x-axis. You can see from around about the 1980s through to 2020 or so, and then the uncertainties are represented by the horizontal extent of the box. And there are quite large uncertainties. So each of these boxes is a separate study that's attempted to estimate the mass balance of East Antarctica. Most of them are above zero. Where those boxes overlap, you could say we're a bit more confident that there's a consensus there and that it has been gaining mass slightly. There's also a couple of studies I've highlighted where these are studies where scientists have tried to reconcile all of the different estimates and come up with a kind of consensus product. And you can see those in the blue and in the black. And quite interestingly, both of them actually have a little bit of mass loss in the last few years or so. So we're starting to see some things happening. But I think one of the reasons we've not been paying attention to East Antarctica is that most of the time it seems to be okay. Another thing is that there's been a long literature about the stability of the East Antarctic ice sheet, which is often played out in some of the earlier literature. We know, for example, that ice has existed in East Antarctica for 15 million years, but that doesn't mean it's always existed covering the whole of the East Antarctic continent. So sometimes that argument about the stability of East Antarctica has been oversimplified, and we've tended to treat it as one large ice sheet. It's there or it's not there, when in fact it's much more likely that some parts had ice for a long time and other parts had lost ice at times. I think another reason we've not been paying too much attention is that when we run some of the numerical computer models of Antarctica, certainly over the next century, East Antarctica doesn't seem to react much to either oceanic warming or atmospheric warming. Of course, that raises some questions. What happens beyond 2100? We need to consider it at those timescales. And also, should we be worried about some of the emerging signs of mass loss in East Antarctica? Because they are there. They've just been uncovered probably in the last 2 decades. Here's a map that's been shown in a few talks at COP this week. It's a really nice example. The blue colors are showing you parts of the ice sheet that are gaining mass. The red colors are showing you parts of the ice sheet that are losing mass. And you can see West Antarctica is covered in red. There's lots of mass loss going on there. But if we look at East Antarctica, there are a couple of hot spots as well. One of those is Wilkes Land, part of Antarctica that seems to have been losing mass for the last 2 decades. And the interesting thing about Wilkes Land is it shares some of the characteristics of those parts of West Antarctica that are losing mass. It's what we would call a marine-based ice sheet, where the ice sheet is resting on ground below sea level, and it's a marine basin that could lead to unstable behavior and a kind of runaway mass loss. There's actually another couple of basins in East Antarctica as well. There's the Wilkes subglacial basin next door, and then there's the Recovery subglacial basin, which I've labeled here. And so if you like, these 3 basins are almost like mini West Antarctic ice sheets within the larger East Antarctic ice sheet. What do these marine basins mean in terms of processes? And Flo will be picking this up in the next talk, but it's worth just thinking about why these basins in particular are sensitive. And there are 2 instabilities that are being talked about by glaciologists at the moment. First of these is marine ice sheet instability, which you can see in the top cartoon here. And what happens here is that if you start nudging the grounding line of the glacier, that junction where the ice begins to float back into deeper water, then you start a runaway process where the discharge has to increase to keep it stable. And if it can't, and if it keeps stepping back into deeper water, you lead to a runaway process. So marine ice sheet instability, it's been recognized since the 1970s. It's been supported by both theory and observations. That bed slope is critical inland. And we think there are even some papers that think it may already have started in West Antarctica, and it may be irreversible once you've started until the ice sheet reaches some higher bedrock inland. There's also high potential for it in East Antarctica as well, in those marine basins I mentioned. The other instability that's much more recently been proposed and is supported by some observations and some modeling, but it's perhaps a little bit more in its infancy than marine ice sheet instability, is that you remove ice shelves very rapidly, perhaps through pooling water on them, and that water can refreeze, it can seep into crevasses, it can fracture the ice sheet apart. We call that hydrofracturing. And so there's another mechanism here whereby if you can remove the ice shelves very rapidly, you expose a very steep cliff at the grounding line. And if that cliff is above a certain thickness, it becomes almost like a kind of coastal cliff. It becomes unstable and topples into the water, and that can run away. Doesn't necessarily need a reverse slope inland, but if your ice sheet thickens inland and you expose it, you will start to see ice cliffs failing catastrophically. So these two instabilities are very important, and they could be important to East Antarctica. Some of the work we've been doing in East Antarctica is looking for those early warning signs that things are happening. And I think Denman Glacier is one glacier that we need to keep an eye on. You can see in the location map where it is. You can see this rapidly flowing outlet glacier, and its catchment contains about 1.5 meters of sea level rise. And we've observed this glacier grounding line retreating inland along a reverse sloping bed very rapidly. And we've also seen its flow speed increase by 25% over the last few decades. And there's a small graph here that you may be able to see that shows that this is a glacier that has all of the ingredients set up for a marine ice sheet instability, in that it's stepping back into deeper and deeper water. I think Cook Glacier is another glacier we need to keep an eye on. Again, it drains a large marine basin, which you can see in the top panel. In the bottom panel, you can see the high velocities in red at the moment, and you might notice that a chunk of the ice shelf was lost. We think sometimes in the late 1970s, early 1980s, Cook Glacier lost an ice shelf, and it's never grown back. And our work here showed that it increased in speed, it doubled over that time period. And of course, what we can do with a numerical model is we can try and get the model to reproduce those observations. So we set the model up in the 1970s, we take away the ice shelf, we reproduce the speed up. And then, of course, the interesting thing is say, well, what happens if we continue to retreat the grounding line of this glacier? And what we saw is that if you just retreat the grounding line a little bit further, you'll see a 300% increase in ice discharge from Cook Glacier. And there's been some other studies on this glacier as well that says, again, it's got all the ingredients for a runaway contribution to sea level rise that could be of the order of 3 to 4 meters. Vanderford Glacier, just one more example that we've been looking at. Vanderford Glacier, we know from ocean observations, has some of the warmest waters in front of it anywhere in East Antarctica. And in the top right panel there, you can see the satellite image of the glacier, but you can also see that deep blue trench, which allows the warm water to get right up and underneath this glacier. And it's actually experienced, or our observations show, it's experienced the fastest rate of grounding line retreat anywhere in East Antarctica. So this is retreating somewhere about 770 meters per hour. So almost a kilometer a year, this glacier is stepping back, again, along a reverse sloping bed. It's not quite as steep as Denman or Cook, but it's on a gentle reverse sloping bed. And then it steps back into a much deeper basin. And then some of our observations have confirmed the grounding line retreat on the left-hand panel there, but also that the ice surface elevation is thinning moderately, just inland. So again, it's showing all the signs of an emerging instability. One of the other things we've been looking at is surface meltwater. I mentioned that might be important in terms of hydrofracturing. Several ice shelves in East Antarctica have large volumes of meltwater on them. And this is something that I think has just started to be recognized in the last few years. We counted over 65,000 of these meltwater lakes in Antarctica back in January 2017, some of them on potentially vulnerable ice shelves. and we know that surface melt will increase in the future. So this plot here shows you the current melt on the Greenland ice sheet, current melt rates, and then the map of Antarctica on the right shows the melt rates projected in Antarctica in 2100 under a high emission scenario, just demonstrating that it will start to look a lot more like Greenland in 100 years or so if we don't start to keep a track on our emissions. And some of the ice shelves in East Antarctica show some of the highest melt rates and could be vulnerable to hydrofracture. Just one slide as well, just showing you that actually in the past, we do know that East Antarctica has collapsed, or parts of East Antarctica have collapsed. So the paleo evidence, when we go back to some of those past warm periods, you could take the mid-Pliocene about 3.5 million years ago, and you can see that atmospheric temperatures were just slightly warmer, 2 to 4 degrees. Sea levels were 10 to 25 meters higher, and we're fairly confident that East Antarctica contributed to those high sea levels. 400,000 years ago, marine isotope stage 11, only slightly warmer than present, and we still think that East Antarctica, parts of it retreated several hundred kilometers inland, could have contributed 3 to 4 meters to global mean sea level at that time. So the key message from these past warm periods and some of the reconstructions that have been done of Antarctica in the past show that it's very sensitive to even moderate warming scenarios, the warming scenarios that we might see in 2200, 2300 if we don't curb emissions. And so just to end then, what we did in the paper was that we looked at all of the published projections of East Antarctic only contributions to sea level rise. So these do not include Greenland, they do not include West Antarctica, they do not include mountain glaciers. We wanted to isolate what was going on in East Antarctica. We looked at a number of published studies, and in some cases we had to reanalyze some of the data and process it, and in other cases we used some of our own unpublished data from the authors that are on the paper. And there's a lot of information on these graphs. Each of those lines represents a different study. Of course, what you can also do is you can play around and you can isolate some controls. So you could use a high melt scenario or a low melt scenario. You could change your climate forcings, and you get a range of different estimates. And our 5th to 95th percentiles at 2100 were -4 centimeters. So actually, I guess taking water out of the oceans up to 22 centimeters. So, in some ways that's showing some of the uncertainties here inherent in some of the modeling. There's a 1 in 20 chance that it could be 22 centimeters, or a 1 in 20 chance it could be -4 centimeters. And you can see here, if you adjust some of the melt sensitivities, you obviously get higher rates of sea level contributions. It's also worth noting that some of those instabilities were built into some of these models. And so we can compare models that include those instabilities and those that don't. And one of the outcomes there is that you can clearly see that they lead to much higher sea level rise estimates. So we can't rule out at the moment, based on current understanding, that East Antarctica's contribution could be over 40 centimeters at 2100, if some of those instabilities, which I've just talked about, actually continue and play out over the next few decades. But I guess our overall conclusion here is that we expect a slightly positive contribution of around 2 centimeters by 2100. Looking further ahead, the top panel shows 2300, the bottom panel shows 2500. And unfortunately, there are far fewer modeling studies to base some of these results on. But you see a much clearer divergence between low emissions and high emissions. So in the low emissions, if warming continues on the high emissions, you see 1 to 3 meters of sea level rise from East Antarctica by 2300, and possibly up to 2 to 5 meters by 2300. But if we look at some of those low emission scenarios, RCP 2.6, that limits warming to around 1.8 degrees, or at least less than 2 degrees, then the East Antarctic contribution would remain below 0.5 meter, even at 2500. I think one of the nice things was there was a paper came out a couple of weeks after ours, completely independently, that reached almost the same conclusion. This paper was looking at core global tipping elements, so components of the Earth system where there are thresholds that might tip them over into instability. And East Antarctica's marine basins, which we've just been talking about, were added to this list of global tipping. So there's coral reefs on here, there's rainforest, there's the boreal tree zone, etc. And East Antarctica has now been added to this. And their conclusion was that it had a minimum threshold of around 2 degrees C, so that in some ways, that's the Paris Climate Agreement scenario, try and keep it to below that. A central estimate, so a best guess that it would become potentially unstable at 3 degrees. And the timescale of response was estimated to be about 2,000 years. So that it would take a long time, but it could be as little as 500 years. It could be up to 10,000 years. But it was quite interesting that an independent study had added East Antarctica to their list of major global tipping points. They even added the whole East Antarctic ice sheet, but suggested that it would need 7.5 degrees of warming. And I guess I just wanted to end as well by pointing out that I've only been talking about East Antarctica's contribution to sea level rise. And of course, Greenland and West Antarctica are at the very left-hand side of this plot. And possibly, certainly with the case of Greenland, may have already tipped over that threshold. So I shall finish there, and I'm happy to take any questions now.
Great, thank you for your interesting presentation. We can take some questions now.
Thank you, Chris. That's great talk. Sorry about my voice. I'm really interested in this talk. And I have two questions. The first question is like, what's the key question you think we need to answer in the next few decades about the East Antarctica? The second question is about the observations. We all know that it's quite limited in the East Antarctica. And also in some special area you mentioned in your talk, like the then and also the Cook Shelf area. I want to know like with the bigger the challenge for us to fill the gap between our modeling work and also the field work. Yeah.
Okay, I think they're great questions actually, and I think they're related. I think one of the largest uncertainties in some of the modeling, and I think Flo will talk about these in a minute as well, is how sensitive you make your model to ocean warming. You know, this is coupling what goes on in the ocean to what happens at the grounding line and with ice shelves, and some of the dynamics there are some large uncertainties there. So I think part of the problem is that we sometimes don't know how sensitive to make our models to ocean warming, and we also don't know how much the oceans around Antarctica might warm anyway. So I think they're two big uncertainties, and that leads me on to your second question, which is what kind of observations we need. I think particularly around East Antarctica, we really need observations of the temperature of the oceans and the ocean regimes, and how often and how much those warm water currents are getting onto the continental shelf and, if you like, eating away at parts of East Antarctica. So I think we need, unlike West Antarctica, we have very few observations of the oceans around East Antarctica. I think another thing we could do more in East Antarctica, which is more difficult to get to logistically, and might be another reason why there's been fewer research papers on there, is that we could do some ice surface elevation data in the past as well. So trying to constrain how thick the ice sheet was in the past and how rapidly it changed and thinned during past warm periods. Perhaps using ocean sediment records as well to try and quantify the rates of change and the timescales of change using empirical evidence would be really important as well. Does that answer your question? Okay, thank you.
Any more questions before we go to our next speaker? I have a short question.
Okay.
When comparing West and East Antarctica, how to control the elevation differences? Because the average elevation difference on the whole dome on the eastern side could have I don't know, maybe an effect in controlling certain variables for the accumulation or the mass gain. So do you consider this elevation effect to maybe normalize both sides?
Yeah, I think some of those accumulation and elevation feedbacks are built into most of the models now. But you're right that East Antarctica is far higher, it's far thicker, the ice is thicker, and there are some competing processes under a warming climate. So we know that parts of East Antarctica are gaining mass at high elevations because the warmer atmosphere is holding more snowfall, if you like, onto the ice sheet. So really in East Antarctica, it's going to be a balance between the additional snowfall and the mass loss. And of course, the worry is that the additional snowfall will not be enough to compensate for the mass loss at the margins. Whereas I think mass gain in West Antarctica is not going to be as much of a compensating effect. Okay.
Well, thank you very much. Okay, great. Now for our next speaker, we will welcome Florence Coglioni from the Scientific Committee for Antarctic Research, and we will continue talking about the importance of the Paris Agreement and its connection to the sea level rise. So, welcome, Florence.
Thanks, Sebastian. So actually, what I really wanted to talk about right now is only paleoclimate. I mean, perhaps that's the first time in this COP I'm able to talk not about future projections, but I really wanted to give a perspective about marine ice sheet instability, because Chris has been mentioning a lot marine ice sheet instabilities. I've been talking a lot also about marine ice sheet instabilities' importance for the future projections. But I wanted to show you this time uh, the evolution of marine ice sheet instability through time, how it comes to be what it is right now, because it's important to understand why Antarctica is so sensitive. So I go briefly to that because Chris has been already explaining most of the stuff here. Um, part of Antarctica is resting on a bed that is below sea level, so it makes it very sensitive to oceanic warmth. And all those sectors are marine-based sectors where the ice shelf, if they disintegrate, because of ocean warming below the ice sheet, could really trigger very much sea level rise. So marine ice sheet instability works this way. You have intrusion of warm water below the ice shelf. Okay, the ice shelves are thinning. Because of the thinning, the inland flux is not able to sustain the platform that floats on the ocean, and so it disintegrates. And to find a new stability, the ice sheet's grounding line, okay, which is, as Chris explained, the junction between where it touches the ground and it starts floating, has to step back in terms of dynamics. And then this is where you lose a lot of ice and rise sea level. We have another instability that somehow complement the first one, which is due to surface melt. If the surface melt penetrates into the crevasse, okay, it is possible to then, during winter frozening, to enlarge the crevasse again and leads to a massive disintegration of the ice shaft, in addition to the marine ice sheet instability. How does this instability, what is the timing of this instability? So such instability occurs on timing of a few centuries. Sometimes can be very quick, sometimes very a bit more slower. So they have a fast trigger about oceanic warming and atmospheric warming tipping points, okay, that can be triggered within a decade, as we are now approaching probably some of the tipping point. And the consequences, on the contrary, is on the long term, because even if the ice shelf disintegrates and to find a new equilibrium, it takes anyway a few centuries until the Antarctic ice sheet stabilizes. And when we take ice sheet simulations, well, we can definitely see that it took 2 to 3 centuries, I mean, to reach a new equilibrium and disintegrate part of Antarctica. What are the ingredients for marine ice sheet instabilities? And okay, so the first one is to have a subglacial bed that is below sea level, okay, because it needs to be where the ice anchors and be vulnerable to ocean warming. The second one is to have a bed that is sloping inland, because if the slope goes inland, when the ice shelf disintegrates, the grounding line step back, and the fact that the slope of the bed below is inland just further accelerates the process. So it creates this runaway process until it stabilizes to a new pinning point on the bed. Third ingredient is, of course, to have ice sheet and ice shelf especially. And the fourth ingredient is to have warm water intrusions. Okay, all those ingredients are necessary to trigger a marine ice sheet instability. Okay, let's take the first one, a subglacial bed that is below sea level. So not all the Okay, not all the glaciers rest on a bed that is below sea level, and when a glacier advances, actually, it erodes the bed. Okay, and it carry on sediments until it stops. For example, in the case of Antarctica, at the continental shelf break, part of the sediments are deposited on the continental slope after the ice sheet reached the margins. Part of it instead are deposited in a form of frontal moraine when the ice sheet is retreating back. Okay, all those sediment deposition forms, they contribute to the building of the continental margin of the Antarctic ice sheet itself. So we have erosion process and deposition process. Okay, this has been happening since 34 million years ago. Okay, at the beginning, Antarctica was not existing. Okay, this is one of the bedrock construction. So what is below the ice sheets? Okay, that we have been trying to do within the paleoclimate community. As you can see within the cycle, I indicated the marine-based sector of Antarctica that so means nowadays are below sea level, but at that time were above sea level. Okay, and it has been eroded. Then with other reconstruction, little by little, advancing and retreating glaciations after glaciations, Antarctica slowly eroded the bed. Well, sorry. Ah, sorry. Okay, let's go back. Okay, it's blocked now. Okay, so until we reach this present day configuration, where we see that most of the bedrock that was in the orange cycle was exposed or above sea level has become below sea level. Okay, so this impacted a lot on the Antarctic ice sheet evolution, even under different climatic conditions. The second ingredient was to have a sloping bed inland. Okay, this is a section, okay, taken across one of the sector of Antarctica. Actually, in the map that you see on the of Antarctica of this over there, you can see all the yellow lines that represents all the data that we have been collected with international projects with marine seismic. Okay, so marine seismic is like echo sounder that allows you to see what is below and beyond the seafloor. Actually, okay, the more beyond the seafloor we go, and the more back in time we go. So we can see all the deposition of sediments that is below the seafloor. And by studying the geometry of deposition, we can understand how the ice sheets evolved by itself. So that's a vertical section across one of the continental margins around Antarctica. And when we interpret it, okay, if you look at the black thick lines, actually, you can see they represents the past bathymetry at different periods. Okay, but what you can see is that if we start from the bottom, you see that the profile is oriented toward the ocean. Okay, in this figure, the ocean is on the right for you, and the ice sheet is in the left. Okay, so you can see that the black thick line are oriented toward the ocean. So at the beginning of the Antarctic ice sheet history, most of the bed was seaward deepening. Okay, and then little by little, okay, by eroding and transporting the sediment and constructing the continental margin around itself, this profile, you can see that it became, at the end, in the blue package, landward deepening. Okay, and so you can imagine that at the beginning of the Antarctic ice sheet history, but most of the bedrock was exposed above sea level, very few ice shelf anyway, because the climate was very warm. So we had little potential for marine ice sheet instabilities. But the more the Antarctic ice sheet has been developing, so eroding, transporting, eroding, transporting, eroding, transporting, the more it has been creating its own settings for being very sensitive to ocean warming. So when we put the different bathymetry at different time periods within an ice sheet model, and we try to measure the sensitivity of the various sector to oceanic warmth, this is how it goes. Those colors shows you the increase in sensitivity of the various sector of Antarctica for the 4 bathymetric configurations through time, starting from the oldest one, so exposed to, with bedrock above sea level, to the present day one, which is the last one. You can see that at the beginning, most of Antarctica is blue, which means a very low sensitivity to oceanic warmings. At the end, I mean, so nowadays, okay, most of Antarctica is sensitive to marine ash sheet instability, because most of the bedrock now is, except the very most inland part, is below sea level. Okay, so the study of Antarctic history about how the bed evolves also tell us that the tipping point for marine ash dust instability has been changing, because before there was no potential for it. Then the more we have been progressing in the history, and the more it has been becoming sensitive. And so when we try to simulate the ice sheet thickness, and try to understand which are the sectors that are vulnerable to high CO2 emissions, well, you can see definitely that the sectors that collapsed at the various periods are the sectors that Chris mentioned. Of course, West Antarctica, but in the East Antarctica, you can see that most of the basin that Chris was showing before are that were collapsing are the one that collapses. And the more we go toward present day, and the larger is the sea level contribution to this kind of collapse. If we rise, sorry, it's overimposed. Okay, if you rise the CO2 concentration to 800 ppm, okay, what the contribution is even larger. And you can see that compared to the first frame on the left, well, the last one, which is present day, has much less ice on the Antarctica. So it means that through time, of course, because of this growing potential for marine ice sheet instability, we have been also increasing the Antarctic contribution to sea level rise, arriving to a configuration now that is ideal for the massive discharge that we are projecting into the future. Fourth ingredients, the intrusion of warm water, okay, warm oceanic water. This is important because without the intrusion of warm water, we do not have any triggers for marine ice sheet instability. So if we look at those climates where the most of the bedrock was exposed, not completely below sea level, okay, climate was also much warmer, 5 to 9 degrees warmer than it is today, with a CO2 above 500 ppm. Well, you can see the red arrows that shows the transport of warm water below the cavities, okay? What is really important in this picture is that the wind system pushes the warm waters inside the cavity. Wind system here is represented by westerlies, okay? And easterlies, which are more coastal winds around Antarctica. Okay, now, at that time period, of course, if the ice sheet reached the coastline, the ocean was 6 degrees warmer than it was today. So there was even no possibility for ice shelf to expand because the ice was melting right away anyway. So no marine ice sheet instability possible. And now if we are moving to the more recent periods where most of the bedrock now is eroded and below sea level, climate is much cooler because we have CO2 concentration at those times that are at 300 ppm, okay? The continental margin has been changing as well, because we have been seeing that before it was seaward deepening and not so much expanded, and it becomes landward deepening and very much expanded, which prevents most of the intrusion of warm waters right now, much more than it was at the beginning, because before it was seaward deepening, so it was a direct access of warm water to the ice sheet grounding line. Now we have a landward deepening profile, which is also more shallower, so it prevents much of the intrusion. So to do that, you need really to have an extreme warmth that enhance wind circulation around Antarctica to push the warm water within the cavities. Okay, so comparison with the previous period, the red arrows are a bit smaller, okay? But the difference is that now you have the bed that has all the configuration to trigger a marine ice sheet instability and runaway process, which you didn't have before. So you have a cooler climate, but more potential for marine instabilities when it happens, and compared to previous period where it was warmer, but less potential for marine ice sheet instability. So that's very important, because it means that if we overshoot temperature, oceanic temperature, then the ice sheet is very sensitive to the first changes and retreat of its grounding line, though the overall global climatic context is a bit cooler than before. Of course, another trigger of pushing the warmth toward the Antarctic ice sheets, it's all the connection to the global climate, because Antarctica is not alone in the global system, okay? Antarctica, I mean, depends on everything that's going at global scale. And for example, if we melt Greenland enough, it might slow down a bit the heat transport, the thermoline circulations, and because of that, all the heat is transferred back to the southern hemisphere, okay, and which triggers a series of processes that enhances the potential for marine instability around along the Antarctic coastlines. So if we usually when we talk about Antarctica or Greenland, it's seldom that we talk about Antarctica and Greenland together, but the system is all together, okay? I mean, the Greenland and Antarctica coexist in the same system right now, so they have some feedbacks, okay? What we see from the paleo data is that once Greenland starts to melt, Antarctica is not melting yet. A few centuries to 1 or 2 millennia after that, Antarctica has massive retreats and massive release of icebergs. This is what we see in the paleo data. Okay, so this loop is definitely existing. We have seen that from ice core records point of view, so comparing Antarctic and Greenland ice core records together, and comparing sediment core records around Greenland to sediment core records around Antarctica. So we know that this loop works this way, also in climate models. So yeah, as I say, we do have evidence of marine ice sheet instabilities. It's not only that we have been observing the margins, the morphology, but we also do have the evidence in the paleo records, just because, as we say, as I explained before, when the ice sheet retreat, it deposits some sediments in terms of frontal moraine that we date back. And this is how we know how much time it takes for a glacier around Antarctica to retreat. We are not able to do that everywhere because it means that most of the data has to be preserved, and we also have to find them, which sometimes is a bit tricky. However, when we find them and are able to date them properly, then at that point, we are able to measure the time it takes. And these are the evidence, the geological evidence we have of those marine ice sheet instability. So some in the western part of the Antarctica and some in the eastern basins, also from Antarctica. So now we are starting to see around Antarctica because we know what to look for also when we go for a campaign for geology. We're starting to observe those marine instability in the past much more frequently in different sectors of Antarctica, and definitely the ones that are already now showing some signs of weaknesses. So, well, this is to show you a perspective about when those events of marine ice sheet instability happen, actually. This shows you the reconstruction of CO2 concentration in the past, okay, from when Antarctica started to glaciate 34 million years ago up to today, and showing you the projections also for the future. So first time we observed in the geological records a collapse of some sectors of Antarctica, it was during the Miocene when CO2 was above 500 ppm and the global mean temperature was warmer by 5 to 9 degrees. Then the sectors that we were mentioning collapsed, okay, all the marine basins, even though they were less marine basin than today anyway. Then it also occurred during the Pliocene 3 million years ago with a CO2 concentration a bit higher than 400 ppm, so basically what we are observing right now, but a global warming about 2 to 4 degrees higher than today. And same thing there, the bathymetry already was very well marine based, and so most of the marine based sector already collapsed at that moment. Then we observed also some marine ice sheet instability when, in the recent interglacials, when CO2 concentration was 300 ppm, was about 300 ppm and a bit lower actually. And at that moment, also some of the marine basins were also collapsing. So that's interesting because we are trying to reach the Paris Agreement, which would imply to go back to a concentration of CO2 in the atmosphere well below the 400 ppm. But even though at this period, because of the feedbacks with oceanic circulations, some of the basins were collapsing anyway. So it's practically obvious that in the future, with a CO2 concentration above 500 ppm, and I am very let's say, conservative saying that, because in the worst case scenario, we are reaching well above 1,000 ppm by the end of the 21st century. It's practically I mean, in this perspective, it's practically likely that some of the marine-based sector will become so sensitive that they will definitely start to retreat. In terms of sea level range, same thing. So if I sum up here, for this Miocene period, the range of sea level rise was about 20 to 30 meters higher than today, okay? So I don't decline all the temperature because I already did it for the same period before. Then for the Pliocene, it was about 15 to 20 meters. Then for more recent interglacial, anyway, we are around 15 meters. More recent interglacial, we are anyway around 5 to 10 meters, let's say, in the range. And this is our projection of the worst case scenario. So when you look at this paleo perspective, well, this becomes obvious that even the worst case scenario is not science fiction in this kind of things. What is very important is that if now we stop, for example, warming our system, well, the ice sheets, as the oceans, are two components that have a very slow thermal inertia, which means that they absorb the heat on the very long term, and they also release it on the very long term. So even if we stop warming it right now, and if we see our ice sheet retreating right now, several decades to several centuries, I would say, later, the ice sheet will still retreat, even though the climate could be cooler. Okay, and we also see that at paleoclimate scale. That's the famous delay between the forcing and the response of a component in the climate system. So in the case of an ice sheet, it will be retreating for several centuries to a couple of millennia anyway, because of the warmth that it has been absorbing, and because of the warmth that the ocean has been absorbing and bringing to the Antarctic margin anyway. So when we try to understand long-term adaptation measures, for example, in the future, we have to account for the fact that the ice sheet has already been absorbing a lot of heat so far, and it will continue to do so. And the same for oceans, which are two ingredients of marine ice sheet instabilities anyway. So our sea level commitments will definitely depend on how much and how fast we mitigate our emissions. We cannot avoid the fact that the ice sheet will still continue to contribute to sea level rise, but we can definitely limit the contribution, which is what Chris was mentioning before, that if we stay well below the Paris Agreement target of 1.5 degrees, we can limit it, not avoiding it. But then adaptation becomes more doable than adapting to an emergency, a multimeter sea level rise with a very fast rates of sea level rise, actually. So, with this talk and with Chris' talks, I think wanted to show that relying on paleo data is really important because it provides you a perspective that is completely different of if you would have been considering only a few decades of data. So the long term is really complementary to the short term observations. It's very hard anyway to bridge them together because the paleoclimate has its own flows. You have to find very high resolution of archive, high enough so you can compare directly with present day variability. However, it's becoming more and more doable, and we are doing this exercise more and more. So what we are trying to do with the new research car program is trying to bridge the communities together that so far goes on parallel ways, let's say. But now we need to bring that together because there is no possible way of directly observing marine ice sheet instability today, but we need to calibrate the physics of the ice sheet model to reduce the uncertainty on sea level change. To do that, the only thing we have is to rely on paleo data. So this is what we will try to do on this program. It has been kicked off 1.5 years ago. It's a multidisciplinary program because Antarctica is in the system with atmosphere, ocean, and the rest. So we have to account for all the feedbacks to understand very, very well how Antarctica evolved in the past and how it can evolve also in the future. So with this program, we already have a huge community committed to it, almost 400 scientists. So we hope we'll have a big conference next year in Italy. So we hope to be able to trigger some debates about the main points that are still weaknesses for, let's say, constrain a bit better the uncertainty on sea level projections. Thanks.
Thank you very much, Florence. So we can get some questions from the audience.
Massive info.
Thank you. So I found it very interesting as a scientist, definitely. Of course, there is this message that the slope becomes more retrograde with time. It has nothing to do with today's policies. However, is there evidence that the ice sheet starts to respond faster as this slope evolves with
Yep.
time? Yeah.
Yeah, definitely. Yep. Yeah, because it's going in the in the direction of the retreat of the grounding line. So as soon as the slope just starts inverting, it's just jumping back each time it can disintegrate. So yeah. So we see a tipping point in the sensitivity of Antarctica around the Pliocene. Yeah.
I have a short question. So you touched the subject of the thermal inertia, which is an interesting thing because sometimes it's assumed like a constant, like physical bodies will remain the same. Yes. So in this, my question is in regard with the Antarctic circumpolar current, because in some diagrams it's just put there like a lonely spot,
Yep.
but what's the assumption of its likely evolution when everything else is changing?
Yep.
Because upon temperature changes, there might be a shift in the submarine elevation of the current. I don't know. So, what's your opinion on this?
Yeah. So, well, it's not only about temperature; it's also about salinity. So, well, right now there is a big wall around Antarctica, which is in terms of salinity, which determines the position of the polar fronts. Okay, and this one is a salinity barrier. Okay, and Antarctic circumpolar current is kind of shallow compared to this one. Okay, because it's wind driven. So what happens is that in the future, we're not sure because climate model diverge on that, but the westerlies, which are the wind that drives the Antarctic circumpolar currents, they changes a bit the locations. I mean, actually, there are two branches of the westerlies. So it seems that one weakens and the other strengthens. So the northern ones should weaken, and the southernmost branch of the westerlies should strengthen. So some models say the Antarctic circumpolar current should strengthen. There is also a possibility of geographical shift, slightly geographical shift of these westerlies. So it would bring more warm water toward the coast of Antarctica. However, with more fresh water around, the salinity should also play a role in, let's say, stopping from Antarctic bottom water formation, which is the response to advection of warmth to the Antarctic coast, actually. Because when you bring the warmth there, you melt more ice, but you form also more sea ice. So you form more dense water at some point. But if it's fresher, it doesn't sink enough to become an Antarctic bottom water. So Antarctic circumpolar currents, according to some other, is going to strengthen. According to other, could also weaken. Where not all agree on that. But as present day, because the oceanic basins are not changing too much, it should not change too much from how it is today. Now, if we take some past periods, of course, it was very different because the morphology of the continental margin around Antarctica was also different. So the position of the main gyres were different because Antarctic circumpolar current was also closer to Antarctica. So there have been some changes in the Southern Ocean evolution as well. But in the future, it's more about strengthening or weakening the strength of the current and freshening the waters.
Okay, great. Some last question? Nope. Well, we can thank our speakers for this session, and yeah, it was very interesting. So, thank you.